Hello everyone. In the last class we have done up to question number 43. Now let us begin with potential energy stored in a spring. According to Hooke's law, if a spring is extended by x due to this external deforming force F, then this external deforming force F will be equal to minus k of x, where k is a constant that is related purely with the spring and it is also known as spring constant k. And what about the energy store? We do know that spring will always have its potential energy because this external force applied will be conservative in nature. Conservative means it will depend upon the initial and the final position. For better understanding, if the spring is elongated by 1 centimeter, we will be requiring only less amount of force, and if we have to extend or if we have to increase the length of the spring by 20 centimeter or 30 centimeter, we have to apply more force. That means this force will be directly proportional to the displacement produced, so it will be dependent on the initial length and the final length. Therefore we can say that the force that is being acted on the spring is always conservative in nature. Therefore it will always have its potential energy, and the potential energy will be equal to half k x square. Remember only these two formula. Other than that, you just ignore it. The force that acts on the spring will be equal to F equal to minus kx. This is known as Hooke's law. And what is the potential energy stored? Potential energy stored for the extension x will be half kx square. And in terms of force F, how will you relate with potential energy? It can be related as half k square x square divided by k, and we do know that k square x square will be equivalent to F. So we can simply put this relation U is equal to half F square divided by 2k. Now let us read the question number 46. Two similar spring P and Q have the spring constant Kp and Kq such that Kp and Kq will have the different value Kp and Kq, but your Kp is greater than Kq. This simply implies that it will be very hard for us to pull out the spring P than that of spring Q. Greater the value of K, it will be more difficult for us to elongate the spring. You should remember this concept. Here we have two spring P and spring Q, and they are elongated by the same amount xx in the first case. Let us read the second statement. They are elongated first by the same amount. Elongated means the amount of extension produced in the spring P and the spring Q are taken to be equal. This is elongated. Spring P is elongated by 3 centimeter. Spring Q is also elongated by 3 centimeter. But what can you say about Fp and Fq? We do not know the value of Fp and Fq, but we do know the value of Kp and Kq. Which one will be stronger? According to the given condition, Kp will be greater than Kq. And what about the second case? By the same force in case B. Let us keep this case B aside. And what is being asked? The work done by the spring Wp and Wq are related. That means we know that work done and potential energy are related. Therefore if we have to take the ratio of these two, potential energy of the P divided by potential energy of the spring Q will be exactly equal to work done for the spring P divided by work done for the spring Q. We know that from our work energy conservation formula, work can be converted into potential energy or kinetic energy, but in this case work done for extending the spring by x centimeter will be will be converted in terms of potential energy. So we can simply use the concept of potential energy stored in a spring, and it will be equal to half k p x square divided by, this will be half k q x square. That means this half and half, x square and x square get eliminated, and we can have wp divided by wq equal to kp divided by kq. And it is also given that kp is greater than kq. That means your wp will be greater than wq. So for the first case, for case number a, we have wp greater than wq. So we can eliminate our option number C and D, because in your option number C we have this wp equal to wq, but this is not obtained in our calculation. Therefore we can eliminate option number C and option number D. What about option number B? If we look at our option number B, it is written that the work done in P is less than work done in Q, which is also contradictory to our calculation. Therefore this can be also be eliminated, and without any further calculation, without even calculating our case number B, we can conclude our answer to be option number A. Anyway, I will calculate for case number 2 also. For case number B, they are extended by the same force. Here this is spring P, this is Kp, and this is force F. And what about your spring Q? This is also again acted upon by external force F. See the basic difference in the question, case number A and case number B. For case number A, they are acted upon by different force, but this different force should be able to produce equal amount of elongation for both the spring. And for case number B, we do not know the elongation. Here elongation will be x1, and next will be elongation will be x2. We do not know the elongation in the two cases. Here this will be kq. And what about the forces? The forces that acts on these two different spring will be of the same magnitude. Therefore we can use the second formula, that is potential energy U is related with half F divided by K. This is the half F U equal to half F square divided by K. This is the second relation, so we will be using here. So UP will be equal to UP divided by UQ, and this will be equivalent to your WP divided by WQ, and we just put the value here. This will be half F. Let me write below here. This will be equal to WP divided by WQ will be equal to half into F square divided by, we will be having KP divided by half F in F square divided by, this will be again KQ. So after simplification, half F square half get cancel out, and we will be having, this is KP divided, not KP, it should be KQ divided by KP. That means finally we get our answer as the ratio of WP divided by WQ will be equal to KQ divided by KP. Which one is greater here? We know that KP is greater than KQ. Therefore your WQ will be greater than WP. Or we can also say like this, WP is less than WQ. Okay, so let us see the option number A. It clearly states that WQ is greater than WP, which is also obtained here. Therefore our answer will be option number A. But in your examination, you do not have to calculate all this, you have to just calculate the easiest part and eliminate the remaining option, and you will get the same answer. Okay, so option number A is our correct answer. Now let us go through our second type, question number 49. There will be two different type of question. There will be asked in your energy stored in a spring. There will be question number 49 and question number 52. We will be doing question number 49 first. For this question number 49, the potential energy of a long spring when stretched by 2 cm is U. Let us suppose this is the spring for this question number 49. If this is the spring, and let us suppose the extension produced is 2 cm. Under this condition, energy stored U is equal to energy stored is U. This will be half into K into this will be 2 square. Let us put this as our first equation. If the spring is stretched by 8 cm, this is the case number A, case number 1. And what about the case number 2? Case number 2 is that if the same spring of here, spring constant will not be changed even though it is elongated by different amount. Initially it is extended by 2 cm. In the final case, it is extended by how much? It is extended by 8 cm, like this from here to here. This is x1. And what about x2? X2 is equal to 8 cm. Then what will be the value of energy? Very simple here. This will be U new energy or energy to U2 will be equal to half. This is K into, we can write like this. This is x2 square. That means it will be 8 square. Can we write like this? This is half into instead of writing this 8 square as half K into, we can write also this is 4 square into 2 square into this is 4 square. Therefore we know that half K into 2 square is nothing but this is equal to U into 4 square means it will be 16. Our answer will be 16U. Option number D will be our correct answer. Next, let us go through our question number 52. For this question number 52, two spring A and B having the spring constant K and the Ka and the Kb, and it is provided that Ka is 2 times Kb. That means our spring A is double the strength of the second spring B, are elongated by applying the force of equal magnitude. If the energy stored in the spring is Ea, then the energy stored in B will be equal to, here they are elongated by applying the same force. Therefore we are going to use the energy stored U is equal to half F square divided by K. Remember this formula. If the two different springs are elongated by the same force, then you are going to use this formula. Energy stored will be equal to half F square divided by K. If we have to find out the ratio between these two, let me put like this. Energy stored in A is represented by Ea divided by energy stored in B will be denoted by Eb, and it will be equal to half, this is F square divided by Ka divided by, this will be half F square divided by Kb, and we do have this half get eliminated, F square get eliminated, and we will be having Kb divided by Ka, and you just put the value here. This will be equal to half Kb divided by, this will be 2 kb, and this kb and the kb get cancelled out, and finally we get our answer to be ea divided by eb equal to how much? This will be half. The energy stored in the A is taken to be EA, then what will be the energy stored in B? Energy stored in B will be very simple. EB will be equal to 2 times EA. So our answer will be option number A. Next, this 6 point article 6.10, it will discuss, or it will be dealing with our last part, that is power. So far we have discussed work done by a constant force, work done by a variable force. We have done that one. And the second will be, the second topic that we have discussed so far is energy, and in this energy concept we have discussed your potential energy, kinetic energy, okay. And the last part will be the power. We will be discussing based on question based on power, and let us discuss what is power. This will be the last part of our work power energy theorem. Here power is nothing but power is the ability of any object to do how much of work. That is, power will be equal to work done divided by time, and we do know that work is also converted in terms of energy. It will be energy divided by time. Generally we can define power as the rate of work done, or rate of energy consumed, or rate of energy produced, and this will be equal to, and this may be also be written as, what is the formula for work? Work will be equal to force into displacement divided by time. We can also put like this: power will be equal to force into, what about the displacement divided by time? If displacement is divided by time, we will be having our velocity. This is also very important, okay. So power P will be equal to F dot V vector. Remember that power will be equal to F V cos of theta, where theta is the angle between the force and velocity vector. So if force is given in terms of a vector form, and velocity is also given in terms of rectangular vector form, then in order to find out the power, you just have to take the dot product between force vector and velocity vector. And other than that, if you want to take only the magnitude, it will be only force into velocity v. That's all. Let us go through our question number 56. We will not be discussing question number 53, 50, 54. I think question number 54 is a similar type of question is being, no, for question number 53 we have done a similar type of question in the previous videos, okay. So we will be skipping question number 53 and question number 54. I will skip these two, and let us go through our question number 56. Question number 56. The heart of a man pumps 5 liters of blood through the arteries per minute at a pressure of 150 mm of mercury. If the density of the mercury is given as 13.6 into 10 to the power 3 kg per meter cube, and acceleration due to gravity is given as 10 meter per second square, then power will be equal to, we have to find out the power of the heart, provided that 5 liter, and we do know that liter is the SI unit, or it is the unit for volume. So volume is given, volume V, volume is given as 5 liter, and we do know that liter is the commercial unit of volume. And in order to convert this in terms of our liter, in terms of meter cube, which will be the standard unit, it will be 5 into 10 to the power minus 3 meter cube. Remember this relation, that 1 meter cube will be equal to 1000 liter. This is very important. you should remember this. 1 meter cube of volume will be equivalent to 1000 liter. Okay, so volume is given. And what about the time, or what about the duration? 5 liters of blood is pumped by arteries per minute. That means our duration time t is 60 second, because 1 minute will have 60 second and time is usually measured in terms of second. Therefore for a minute we just take 60 second. And what about the pressure? Pressure is also given. The blood pressure, BP. Okay, BP means it will be blood pressure. Blood pressure is given by 150 mm of mercury. And here I will give you one simple concept of pressure in a liquid column. Usually pressure can be easily calculated by only knowing the height of the liquid column. Let us suppose this is a vessel, or this is a fine capillary tube, and let us suppose this amount of height is being raised, or this is the raise in the liquid column, or we can consider this is the height of the liquid column. Then what will be the pressure produced due to this liquid column, provided that rho is the density and g is the acceleration due to gravity at this place? Then we know that pressure will be equal to I is rho g. Pressure produced by liquid column will be equal to I is rho g, and we do know that density will not be changed, acceleration due to gravity will not be changed. So if we know the height of the liquid column, then we can easily find out the pressure corresponding to it. Therefore usually it is 150 mm. 150 mm of mercury means there will be a pressure equivalent to 150 mm. Okay, so if exact pressure is not given, they will just give you only 150 mm. Then you have to convert this 150 mm of mercury column into equivalent pressure. Let us find it out. Pressure is equal to I is rho g. You just put the value here. What is the value of ice? Ice is given as 150 mm. Mm means millimeter, and this must be converted in terms of meter, so it must be multiplied with 10 to the power minus 3. And what about the density? And density of mercury is given as 13.6 into 10 to the power 3 into, what about the value of g? The value of g is taken as 10, and after simplification we will be this 10 to the power 3 and 10 to the power 3 will get cancelled out, and we will be having our 150 into this will be 3136. And let us find out the value here. 150 into, or simply 136 divided by 5, it will be 0 5 0 33, 1 in 3 in hand, 15 18 18 1 in hand, 500 5 8. This is 1 13600. This will be 14 11 12 and this will be 2. We will be having 22400. Okay, this will be the pressure, blood pressure. And usually we know the pressure is measured in terms of Pascal. This will be in terms of Pascal. And we do know that power is being asked. Power, what is power? Power will be equal to, very simple, it will be work done or energy, work done. This will be work done divided by time. Very simple. And we do know that work done is also equal to pressure into volume. Pressure into volume divided by time t. Remember that this pressure into volume will be exactly equal to how much? This will be equal to work done. Remember this relation, this is going to be used in our thermodynamics chapter. So pressure is how much? This is 22400. We just write it as 22400. And what about the volume? Volume is 5 into 10 to the power minus 3. 5 into 10 to the power minus 3 divided by, we will be having 60. So this 0, we can have this 5 12s are how much? 5 12s are 60. So 22400 divided by how much? Divided by 12. 12 1s are 12. This will be 0. 0. This is 10. This is 4. And we will be having 12 8 12 9. 12 9s are, let me find it out. 9 2s are 18. 1 in hand. This will be 10. 108. This is greater, so we will be multiplying with 8. 12 8s are 8 1s are 96. It will be 696. Okay, 96. This will be 80. Next will be 12 7s are 84. This is 84. 12 6 12 6, that means it will be 72. And we will be having this will be 806. So we will be having 1866 into 10 to the power minus 3. So we will be having 1.8. Approximately we will be having 1.8. Our answer will be 1.70. This will be 1.866. Therefore it can be approximately taken to be 1.70. They are almost equal. Okay, our answer will be option number C. So answer comes out to be option number C. Now let us do your question number 59. For this question number 59, what is being given? For this question number 59, a car of mass m starts from rest and accelerates so that the instantaneous power delivered to the car has a constant magnitude p naught. Then the instantaneous velocity of the car is proportional to. Here a car starts from rest and it start increasing its speed so that the power delivered by the car has a magnitude p naught, and we have to relate this power p naught with respect to the instantaneous velocity. Simply they are asking us to find out the relation between power and velocity for this specific question number 59. For this question number 59, we have power is equal to, power p is denoted by work done divided by, and this will be time. And we do know that for conservation of work done theorem, we will be having work done equal to change in kinetic energy, because the body started from rest and it goes with some velocity. So we will be applying this formula. Power p will be, what is the constant power? Constant power is given as p naught, and change in kinetic energy will be half m v square minus, this will be 0. Why it is being put as 0? Initial kinetic energy will be 0 because the body has started from rest, so it will be denoted by 0 divided by time t, and we can put the value as 2 p naught t divided by m, and this will be equal to v square. And if we have to remove this square root, then it will be like this, and we can say that the instantaneous velocity is proportional to, we do know that this 2p divided by m are constant, p naught is also constant, m is also constant, so our velocity v will be directly proportional to t raised to power half. Square root means it will raise to power half. Our answer will be equal to option number B. Now let us do one more question. And this question number 64. For this question number 64, we have force vector given as F is equal to 60 I cap plus 15 j cap minus 3 k cap. And what about the velocity vector? This is v vector is given as 2 I cap minus 4 j cap plus 5 k cap. And we do know that for finding out the power, it is very simple. We have to find out the dot product. I will do it in one single step. Here 60 must be multiplied with 2, I must be multiplied with I, j must be multiplied with j. So 60 into 2 will be equal to 120 minus. Why do we take minus? Because j cap is positive in f vector and negative in v vector, therefore it will be 15 into minus 4, it will produce minus 60, and it will be also again minus 15. 3 into 5 15, and here we will be having 120 minus 75, and our answer will be equal to 5 1 in hand, this will be 845. Answer will be 45 watt. That's all. So he after doing this question number 64, we have completed your chapter work, power and energy. Okay, now let us begin with the new subtopic, that is collision. Actually this collision will be studied in our general course or general syllabus as separate chapter, but here for revision I include in your work, power, energy chapter. Anyway, let us begin with this collision. Actually this collision will become under different heading, therefore let me let me make another video for collision alone. So bye for now.